we finished talking about series, just series of numbers, right? So the series that we have been dealing with, they have been of numbers, so sequences of numbers. Now we're going to continue discussing the notion of series, but this time we're going to be bringing variables into the mix, okay? So the point is that now we want to look at series as functions, all right? And let's, whenever we do that, we obtain something that's called a power series, so we're going to define what they are and understand how we study power series, okay? So that's the main idea for today. Okay, so let me begin with an example. And to motivate what we're gonna do. All right, so I gave you a problem a couple of lectures ago. Let's see, what was it? Actually, last lecture, in one of the examples here in the ratio test, there was a problem here that we didn't get time to do, that I asked you. I gave you this series, okay? This is a series, it's just that it has a variable here. And the point is that depending on what this x is, this series may or may not converge, okay? So the question was to actually try to figure that out. So to figure out the values of x for which this series converges. And basically, we didn't do it in class, but then I put here the solution later on. And the idea is that this is a series, so this is your general term. And then we can apply ratio test to this, and when we do the ratio of an plus 1 over an, it turns out that we get this expression, okay? Now, what happens when we take the limit of something like this? Remember, this is something important. The limit is with respect of n, when n approaches infinity. So when you consider this limit, x has nothing to do with n, okay? Now, x can be whatever it is. It's just a number. Remember, this is a variable, but this could be any number you want. At the end of the day, this limit, the top is a number, and the bottom goes to infinity, so this limit is 0, right? So that limit is going to be 0, which is less than 1, and that's true for any value of x. So what does that mean? The ratio test tells us that that series converges regardless of the number that x is, right? You can put here whatever you want, you will get limit equal to 0 anyways, so that's okay for all values of x. And you can conclude by the ratio test that this series will converge for every value of x, okay? I want to expand on this idea today, but instead of doing this example, I'm going to do another one, okay, which is slightly more interesting, and that's going to motivate different ideas that we're going to do. But basically, the point is that now you can consider this as a function. For example, we just showed that regardless of x, this converges. So when x equals 0, you get the series 1 over n factorial. That's going to converge, so that's going to give you a number, okay? So you can think of this as a function where the input is 0 and the output is whatever the series that you obtain converges to. If you put a 2, you're going to get 3 to the n over n factorial. Once again, that converges. Then if the input is 2, then the output is whatever the series converges to, and so on and so forth, okay? So that's why we can look at this as a function. Remember, a function is just a relation that giving an input, it gives you only one output, okay? That's all it is. All right, so let's do something similar, but with a more interesting series. So example is find all values of x for which the following series, so it's going to be the sum from 0 to infinity of x minus 2 to the n, or n plus 1 times 3 to the n, converges. Okay, so what we want is to figure out, we see an x in there, so what we want is to figure out all values of x for which this series converges. Okay, so just like as you saw in the previous example, we're gonna try to analyze this using ratio test. So solution, let's do the ratio test and see what we can do. Okay, so for that, once again, our an, we're gonna use ratio test, and for an, we're gonna take the whole expression, okay? This is our an, so we have to look at the absolute value of an plus 1 over an, and then see what happens. Here you cannot ignore the absolute value because we have an x, and depending on the x, this could be positive or negative. So the absolute value cannot disappear. Okay. So everything will happen inside the absolute value. So x minus 2 to the n plus 1 over n plus 2 times 3 to the n plus 1. And then times, I'm going to flip an. So 3 to the n plus 1 over x minus 2 to the n. Okay, so let's start simplifying here. So this x minus 2 to the n cancel with an x minus 2 to the n over here, leaving me one of these, one x minus 2 in the top, right? So this is gone with this. And similarly, this 3 to the n on top cancels with 3 to the n in the bottom, but it's going to leave me a 3 in the bottom. Okay? And that's it. We cannot simplify anything else. So on top, we get absolute value of x minus 2 times n plus 1 over n plus 2 times 3. So notice that whenever you have stuff that are already positive, you can take them out of the absolute value. So the only thing that we need to keep the absolute value on is on this term right here, the x minus 2. That's the one that we don't know if it's positive or negative because it depends on x. So this would be n plus 1 over 3 times n plus 2 times the absolute value of x minus 2. Okay? I can take this stuff out because I already know this is positive anyways, okay? So no need to leave it inside the absolute value. So this is what we get. So now we take the limit. So limit as n approaches infinity. Remember what the ratio test says. It says, look at this ratio, take the limit, and then if this limit gives you a number, you compare it with 1, right? If it's less than 1, converges absolutely. If it's bigger than 1, diverges. If it's equal to 1, it's inconclusive. So let's compute this limit and see what we obtain. So we have n plus 1 over 3 times n plus 2 times the absolute value of x minus 2. All right, so once again, this limit is about n, okay? So this is the limit as n approaches infinity. And notice that this term right here, the x minus 2, there is no n in here, right? So this guy has nothing to do with the limit. This is like a constant with respect to the limit. Do you understand this? X, when you look at this limit, it's true x is a variable, but it's fixed, okay? X is not changing. You can put here whatever you want, but once you put it, it's fixed. So whatever computation we do, assuming that x is constant, that will be the same thing regardless of its value, okay? So when we take this limit, this part right here is a constant, so we don't have to do anything with it. What happens to this term right here? What is the limit? 1 over 3. So this is going to be 1 over 3 times absolute value of x minus 2, right? Remember, that's a constant. With respect to the limit, this is a constant. So we have 1 over 3 times absolute value of x minus 2, and now the question is, when does this series converge? Well, we do the limit, we get this expression. What do we need if we want convergence? What does the ratio test says? Less than 1. So we declare that this has to be less than 1, and then we solve for x. Okay? This is going to tell you the values of x that will satisfy this inequality. And the values of x that don't satisfy this inequality will give you that it's bigger than 1. So you know it diverges also. The only thing that is left to figure out is what happens when this is equal to 1. Right? Because the ratio test doesn't tell you anything in those cases. So let me say something here. So note the solution to absolute value of x minus 2 over 3 less than 1 gives values of x for which the series converges. By the ratio test. Agree? Now, similarly, as the first point, second point is that the solution to the other inequality, absolute value of x minus 2 over 3 bigger than 1, once again, we give you values of x for which the series diverges by the ratio test. Gives values of x for which the series diverges. once again by the ratio test. So all we need to do, so then point number 3 will be, we need to investigate whenever this equals to 1, we need to investigate this situation. So we need to investigate what happens when absolute value of x minus 2 over 3 equals 1, because we cannot deduce anything by the ratio test, okay? But at least we can do something with the first 2 points, so let's get that out of the way. Okay, so we know that we're going to get convergence as long as absolute value of x minus 2 over 3 is less than 1. This is going to guarantee convergence. So let's solve this inequality. This is a little absolute value inequality. So that means absolute value of x minus 2 is less than 3. So x minus 2 is between 3 and negative 3. And then adding 2 everywhere, what do we get? We get that as long as x is between negative 1 and 5, this series is going to converge, okay? So if you want to think of that series above as a function, this, what you're finding here is actually the domain of that function, okay? These are the values that you can plug in. If you plug in anything bigger than 1 or less, bigger than 5 or less than negative 1, you're going to be on the other situation as we're about to see, and therefore the series will diverge, okay? So far, so what this is telling me from here is that we get convergence. So converges for x in the interval from negative 1 to 5, open interval. This is what we have so far, okay? And also notice that away from this interval, we actually get the opposite, right? So if you do this, bigger than 1, this is what's going to give you divergence, right? Ratio test. We need to solve this inequality, x minus 2, absolute value of x minus 2 bigger than 3. So how do we solve this? That means x minus 2 is either already bigger than 3 or x minus 2 is less than negative 3. So x is bigger than 5 or less than negative 1. In other words, let's draw a picture here. That means, so with this, the series diverges. So let me draw a picture. This is what we have so far. So negative 1 and 5, these are important points. I'm going to put it here, negative 1. I'm going to put 5 here. And what we have seen so far is we haven't said anything about negative 1 itself or 5 itself. But what we have seen is that if x is somewhere in here, so x in here, what happens to the series? Converges or diverges? Converges. X in here, then the series converges. And then what the computation above shows is that if x is in here, what happens to the series? Diverges. Then over here diverges, and over here diverges. Yes? So that means that over the entire real line, among all possibilities that x could be, if it's bigger than 5, it's not good. The series diverges. Less than negative 1, it diverges. X better be between these two numbers. Yes? Okay, now the only thing that remains, the question is, okay, what about this guy? What about this guy? The ratio test doesn't do anything here because at these points, that's when you get equal to 1. Okay? If you put 5 in there, you're going to get absolute value of 3. So 3 over 3, that's 1. If you put negative 1 in there, you get absolute value of negative 3. Once again, 3 over 3, that's equal to 1. So we still need to figure out what to do here and what to do here. Okay? So what do we do? Well, we plug in that value into the series and then the variable disappears and we have a series like the ones that we started in the previous chapter. And we do any of the tests that we know. So let's analyze x equals negative 1. So our series is, so if we put negative 1 here, we're going to have a negative 3 to the n, right? On top. So we're going to have negative 3 to the n. This is sum from 0 to infinity of negative 3 to the n over n plus 1 times 3 to the n. This is what we obtain when x equals -1. Let's see whether this converges or diverges. So what happens here? So that would be 0 to infinity. We can split this as -1 to the n times 3 to the n. These guys cancel, so we end up with the sum from 0 to infinity of -1 to the n over n plus 1. What do we know about this series? It converges in series. It's an alternating series, and using the alternating series test, it converges. This is the alternating harmonic, right? So converges by the alternating series test. Yes? So that means that now we can go in here and fill in this picture with a closed circle. Because now we know that for -1, it converges. Yes? Now let's do this. Let's play the same game with the other endpoint. X equals 5. So what series do we get? So if I put a 5 in here, we're gonna get a 3 to the n on top. Yes? Because we're 5 here for x, you get a 3 to the n. So we're gonna have 3 to the n over n plus 1 times 3 to the n. These guys cancel, so you end up with this series. 1 over n plus 1. What do we know about this?
It diverges using the comparison test.
It diverges. In fact, this is the harmonic series. Remember, the harmonic series starts at 1, but it's 1 over n. But this is exactly the same series, because if you start at 0, and then you're doing n plus 1, what are the terms here? 1 plus a half plus a third, and so on. So that's harmonic, diverges. So this is 1 plus a half plus a third, and so on. So this is diverges. This is the harmonic series. Yes? So that means that remains an open circle. So, summary. So what we have seen so far is that the series sum from 0 to infinity of x minus 2 to the n over n plus 1 times 3 to the n, that's the original series. So this series converges, and moreover it converges absolutely, right? And over here the convergence will be conditional convergence. So a -1 is conditional, but inside is an absolute convergence in the parentheses. Okay, so this series converges for x in, so what will be the interval? Square bracket -1, 5 parentheses, right? It will converge on that interval. Do you understand this? The bracket and the parentheses?
Yes.
Okay, converges in this interval and diverges for any other value of x. Yes? So we answered the question. Now what I want to do is, first of all, if you have questions, ask me, and then I'm going to revisit this example, and there are some names that I'm going to assign to each of these things, okay? But before I start talking about that, do you have any questions on what we did? So basically we just did ratio test, right? And you know, the important thing here is that when you do ratio test, don't ignore that there is an x, okay? And when you take a limit, you need to understand the limit is about n, not about x. Therefore, x is considered a constant with respect to this limit. So you just take the limit of whatever has an n. In this case, this piece was 1 over 3, so the limit is 1 over 3 times whatever this is. Yes? So once you get here, then remember, our job is to analyze convergence. Our job is to analyze convergence. So because we're trying to do ratio test, that means that we need to take this result and compare it against the number 1. And as you know, if it's less than 1, it will converge. So when you solve that, it tells you that x better be between -1 and 5, right? If it's bigger than 1, it will diverge. So that means away from that interval. So we already get a picture like this one. But still, these two question marks, right? Because the ratio test does not guarantee what happens. It does not tell you what happens here, because at this point that's going to get equal to 1. So how do we analyze this? You make x equal this number, plug it in, you get a natural series, no variable involved. Analyze it with any of the tests that we know from before. Okay? Then the other one, repeat. So let me actually put here that at this point we get convergence, and now this one we get divergence. Okay. All right. So what that means is that because this has a variable, it has an x, we can now look at this as a function. Okay. Where the domain of this function is this interval over here. Remember, the domain of the function, these are the values that you're allowed to plug in into the function, right? And that means that for each x here, when you put it in there, you're going to get an output. You're going to get a number because the series that you obtain will converge. So you can look at it as a function. This interval is the domain of this function. It has a name. This is called the interval of convergence. It's kind of clear why it's called the interval of convergence, because these are the values for which that series converges. Series that look like this, they're called power series. And moreover, this number is special. Let me show you something. Look at the interval of convergence from -1 to 5. What's the middle of this interval? What's the center of this interval?
2.
So 2 is right here in the middle, right? And notice that that 2 is right here. Okay, so we call that the center of the series. So this is called a power series centered at 2. Okay, I'm gonna write all these things in general now, but first I wanted to do an example so you can see it. So this is a power series centered at 2, and the theorem is that this will always be the situation. Power series, they will always converge because they always converge at the center. Okay, the question is, do they converge at values other than the center? If they do, it will always be like this. It's going to be on an interval expanding around the center in a symmetric way. Okay, and then it will converge in some place and not away from that interval. Or maybe it converges on the entire real line. Okay, so this is the center, but it expands indefinitely to the right and to the left, like the first example that we did. That we get that the limit was 0 regardless of x. So in that case, the interval of convergence will be from -infinity to +infinity. So that's the center. We call this guy the center. And another thing to observe, how much is this distance?
3.
3. How much is this distance?
-3.
Distance.
Oh, 3.
3. Because this is symmetric. That number 3 is called the radius of convergence. Okay? Because that's the radius of your interval. Okay? So you can find the radius. Once you have the interval of convergence, just take the endpoints, add them, and subtract them, right minus left, and divide it by 2. And that's going to give you radius of convergence. Okay, you look at the distance and divide by 2. So the interval -1, 5 is called interval of convergence. Okay, the number 2 is called center of the series. And actually, I should have a sentence here. This is an example of a power series. This is an example of a power series. The interval -1, 5 is called interval of convergence. The number 2 is called the center of the series, and then the radius of convergence is 3. Okay. Moreover, so note that the interval here is -1, here is 5. We have 2 here in the middle. Notice that 5 can be written as 2 plus 3, and -1 can be written as 2 minus 3. Okay? So moral of the story. Once you know the radius of convergence, you immediately get for free the interval of convergence because you have your center, and then you add the radius, you get this point, you subtract the radius, you get this other point. Okay? So the whole point is figuring out the radius of convergence. Once you know it, then you're good to go. I guess, let's see something else that may be relevant. Notice that the radius of convergence came up right here, okay? When you have these three. So when you're doing these problems, you will always have the absolute value of x minus whatever the center is, and then would be greater than or less than a certain number. That number would be your radius of convergence, okay? But my advice is just solve it. You look at the interval and then find the middle, and then you will know the center already. You subtract the right endpoint with the center, and you get your radius, okay? Finding the interval is actually easier, but for theoretical purposes, once you know the radius of convergence, you can immediately build your interval. And then, of course, this doesn't tell you anything about the endpoints, but the endpoints you analyze them individually. Okay? All right. Any questions? Do you understand what interval of convergence? I'm going to write all this down now formally, but first I want you to see, in a concrete case. Do you understand what these names are? Okay. Yes.
Instead of using ratio test, could you use root test as well?
So let's see. For this problem, yes, you could do root test. If you do the root test, you just have to deal with the square root of
the nth root of n plus 1.
Yeah, the nth root of 1 over n plus 1. So the nth root of n plus 1. Exactly, you will have to deal with that one. Because the x minus 2 over 3, absolute value of x minus 2 over 3 will go up. But then when you take the nth root, as you know, it will be equal to 1. So you will end up with the same expression that we did. But yeah, here I use ratio test, but the root test identically help you here because the conclusion is very similar, right? You get your limit and you compare with 1. So it's the same idea. Good. All right, are we good with this? So let me then make this a little bit more formal, okay? So the above is an example of a power series center. Now, this hopefully makes sense to you, why I say center at x equal 2. Okay? It's an example of power series center at x equal 2. So definition. So suppose that we have a variable. So let x be a variable. Then let me rewrite this a little bit. Notice that we can rewrite this as the sum from 0 to infinity of 1 over n plus 1 times 3 to the n, all of that times x minus 2 to the n. Yes? In other words, you can think of this as being the following. If I call this an now, it's not the same an that I call above, okay? So this has the form a sequence times x minus a number to the n power, right? If the center happens to be 0, how would this look like? But remember, this number is called the center. This is center at 2. If the center is 0, this is just x to the n, right? So how does the power series center at 0 looks like? The sequence an times x to the n. Okay, that's the power series center at 0. So let x be a variable, then an infinite series of the form the sum from 0 to infinity an x to the n. And again, all I mean by this is, this is a number, a0 plus a1x plus a2x squared, etc. Okay? So a series like this is called a power series centered at 0. So this is called a power series. So it's called a power series. Let me give you the general definition. So more generally, a series of the form. And then the general one would be like this. You have your sequence, but then x minus c to the n. Okay. By this I mean a0 plus a1 times x minus c plus a2 times x minus c squared, and so on. So a series of this form where c is a fixed real number is called power series centered C. It's called a power series centered C. And then of course C is called the center of the series. So power series centered C, the number C, is called the center. So far so good? I mean, this is exactly what we said above in the example. Okay, so some examples here. Examples. I guess, let's say here, just to make it interesting, find the center. Let's see, I'm going to do the sum from 0 to infinity of x to the n over n factorial. Then the sum from 0 to infinity of 3 times x minus 2 to the n. I mean, we already have the example from before. I'm just putting different ones in here. Negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. These are, I claim that these are power series. Do you recognize them as power series?
Yes. Recognize the first one and second.
So let's see, find the center. Let me say here, find the center and an. Okay, so by an I mean, you know, the sequence of coefficients. Notice that the coefficients here is actually a sequence, right? If you ignore the x part, that's a sequence. Okay, so let's see. What's an? 1 over n factorial. That's a sequence of coefficients. And what's the center?
0.
This is centered at 0. Yes? Good. About the next one? What's an? 3. So it's a constant sequence. It's just 3s all the time, right? And then what's the center?
Negative 2. Or 2.
2. So, okay, let me make it more interesting.
Negative 2.
So what's the center?
Negative 2.
Negative 2. Yes? So the center is, you know, the opposite of what you see in there. Okay? Because the definition has x minus c, and we're calling c the center, not negative c. Okay? And the last one was the sequence?
1 over negative 1 raised to n over 2 n plus 1 factorial.
1 over 2.
Pay attention.
And then we have that x raised to 2.
So the an, right? But what happens here? So this is only taking odd numbers, right? So you cannot tell me that an is 1 over 2n plus 1 factorial. Let's see. Can you tell me that? No, you cannot tell me that. Because these are the only coefficients that we are seeing here are the coefficients of the odd powers of x. How about the coefficients of the even powers of x? Remember, the power series is supposed to be this guy. I mean, the center, we see that the center is 0, right? Everybody okay with this? The center is 0. So it has to look like this. So what we're seeing in there are the coefficients of x, x cubed, x to the 5, and so on. Because you see a power 2n plus 1. But what about the coefficient of x squared? What about the constant term? And so on. Okay? So what happens is that they are not there. So that means those are 0. It's a power series. It's just that the even coefficients are 0. The coefficients of the even terms are 0. The only ones, the ones that are not 0 are the odd terms, right? So you have to be a little bit, you know, to be precise here, the sequence an, this would be 0 if n is even, right?
Yeah.
0 if n is even. And then when n is odd, how does it look like? So if n is odd, that would be negative 1. So let's see, when n is odd, now here we have to When n is odd, the first odd number here is 1, and we get a positive. Then the second odd number is 3, but we get a negative because that's n equals to 1, right? It's just that this n is not the same as this n. That's what I want you to understand. This n is not the same thing as this n. This is the counter for all the odd numbers, and this is the counter for all the integers. That's different. As this n changes from 0 to infinity, you are going through all the odd numbers here, right? But here, as n changes from 0 to infinity, you're going through all the integers. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so you have to be careful. Okay, so here we want to say that the odd numbers are alternating. So definitely, because n is odd, I already know that I need to have an n factorial here. N is odd. Okay, we just need to fix the sign. Okay, so what is it? So let's see. We start with the first one when n is equal to 0. So when n is equal to 1, you're gonna get positive. So when you have the first odd number, you get positive. Let me rewrite this. So when n is equal to 0 here, this is the same as the following sequence. That's just x, then minus, then you have x cubed over 3 factorial, then plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial, and so on. Okay? This is just a way of writing this down. Okay? So it's easier to just analyze this one instead. But the reason why I'm doing all of this business is because, here we are missing the a0 to the a0 term, then we have the x, then we are missing the a2 term, then we have this one, then we are missing the a to the 4th term, then we have this one, and so on. So what we're saying is, okay, we're missing these guys because these guys are 0. Okay? So that's what I'm saying here. When n is even, you get a 0. So that term is not there. So now this is n equals 1, n equals 3, n equals 5. Do you see it? N equals 1, n equals 3, it matches the power. N equals 3, n equals 5, then n equals 7, that's the other term, etc. That's the n that I'm using here. Okay? All right. So this is n equals 1, this is n equals 3, n equals 5. And then I want to create the alternating behavior. So that means it's 1 over n factorial, as you can see, 5 factorial, 3 factorial, and so on. We just need to make sure that we have positive, negative, positive, negative. So we have to do -1 to some power. What is that power? So n equals 2k plus 1, yes, for some k. When n is odd, you can always write it like this, for some k. So let's see, I want to say that this k is going to be n minus 1 over 2. Let's make sure that that's what we want. So when n is 1, my k is 0, and I get positive. When n is 3, my k is going to be 1, so I get a negative. Yes? So the point is that this always works because n is odd, so when you do -1, it's even, so you divide by 2, you will get a nice integer. Okay? So when n is 3, then you're going to get the negative. When n is 5, this is 4, so you get squared, so it's going to be positive, and so on. Okay? So in other words, this k here tells you what term you're looking at in the list of odd numbers. When k is 0, we're looking at the first odd term. When k is 1, we're looking at the second odd term, and so on. Okay? So, to the k, where k is calculated as n minus 1 over 2. It's a little bit more technical, but nevertheless, if we want to do it correctly, this is how we need to do it. So that's a sequence, okay? And then c is equal to 0. Let me write. C equals C. Okay, and this right here is the bottom part was just a calculation. And this is how we define the sequence. So when n is even, you have 0, so that means you don't have none of the even terms. And when n is odd, you're going to have one over n factorial, but it could be positive or negative. How do you know? Well, calculate k. You do n minus 1 over 2. Okay, and you do negative 1 to that power. So, for example, who can tell me what would be a to the 317? Right? So, let's actually 316, and what would be a to the 317? So what's a to the 316?
0.
That's 0, because that's even, right? Now, how do we compute this one? So we need to figure out k, right? So how do you find k? So for this one, how do you find k?
N minus 1 divided by 2.
Minus 1 over 2. So that's 316 divided by 2, what is this?
58.
158? Okay, so that will be negative 1 to the 158 over 317 factorial, which happens to be positive 1 over 317 factorial. If I now ask you for the 319, you're going to get a negative guy, right? And so on. Yes? So, anyways, if the series looks a little bit confusing with the summation, just rewrite it like this, okay? And then analyze it from this point of view. And then here you will realize that you're missing all the even guys, so that means the corresponding coefficients are 0. You only have the odd ones. You just need to think a little bit how to describe those, okay? All right. But again, it's just a fun exercise, but this is not going to be too meaningful for what we're about to do. By the way, one of the upshots, let me just give you a heads up of what's going to be happening in the following sections. As you can imagine, we want to think of these guys as functions, right? So another question is, does this series represent any function that we already know? So is this series equal to some function that we know? Is this series equal to some function that we know? This one, also this one, is this equal to some function that we know? Okay, we're going to learn pretty soon how to do that. For this one, we're going to hopefully discuss it today. For 1 and 3, we need to wait a little bit. It turns out that number 1, I present to you the exponential function. That's e to the x. Okay? And number 3, I present to you the sine function. This is equal to the sine function. In fact, this is how originally those functions were defined. Okay? And this is how your calculators compute those functions. For example, the sine is alternating. Now you know how to approximate alternating series with the degree of accuracy that you want. The computer, when you say sine of 3.5, I don't think it gives you 0.7, whatever, blah, 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 blah. This is what's going on. It's just adding a bunch of terms until it gets the accuracy that it can give you. What's the accuracy? How many decimal places the screen holds, right? That's it. Yes?
Isn't that the Taylor series for sine as well?
Yes. Taylor's Maclaurin series, which
yeah.
is just Taylor centered at 0. So we're gonna give fancy names to these guys later on. That's why I said it's all the same thing. It's not.
I get it.
Okay. All right. Questions?
The only condition we needed to justify separating it into an for even and an for odd is having 2n plus 1 in the main part of the function.
Exactly. You see this guy, and now you see that we only see the odd powers of x. We're keeping all the evens.
Right. Just having that in means the other n negative 1 to the n only matters for our sign. It's not affecting which
The coefficient, the actual value.
yes, it's a coefficient. The actual value is
Exactly. The negative 1 to the n is just telling you when it's going to be positive, when it's going to be negative. That's all. And that's why we needed to play with this k, because the point is that n is the same as this n. I know it looks strange, but that's the same. So, okay. Are we okay with this? Anyways, probably that was a little bit too much for now, but that's okay. That's okay. We're just having fun with the sequence. But like I said, this is not so important for what we're about to do. Okay. What I want you to get from here is that you should be able to see this and say, yes, this is a power series. Yes, I know what the center is. And I want you to realize that it may not be that, usually it is straightforward to figure out AN. Sometimes you have to be careful. Okay, that's the only thing. Okay, so now what else should I say? Well, we can look at these functions now. By the way, I want you to realize that these functions, this series, they always converge at the center. What happens if I plug in x equals c? The center is c. What happens if I plug in x equals c into the series?
We're gonna get 0.
Well, we get all of these terms, they die, they become 0, and we obtain whatever this first guy is, right? So power series, they always converge, at least at the center. The question is, do they converge somewhere else, okay? That interval where they converge is called interval of convergence, so that's what I'm gonna write. I'm gonna give you the theorem that tells you that such an interval always exists, okay? Even if it's just the point C, as you can obviously see. So let me write that down. So right here. So remark, actually, I should, no, let me leave it here. So remark, power series can be seen as functions. Do you understand why I say that they can be seen as functions? Yes? Okay. You know what a function is? Something that takes an input and gives you an output. Yes? Okay. So they can be seen as functions whose domains are all values of x, for which the series converges. And here is a little definition. This is called, how do we call this domain? How do we call these values? Interval of convergence. This is called interval of convergence. So a typical question that you're gonna get is, you're given a power series and then they will ask you, find the interval of convergence. Just like when you were in college algebra, they give you a function and they will ask you, find the domain. That's what we're doing now. You're given a function, the power series in this case, find its domain, which is the interval of convergence, okay? So this is called interval of convergence. Remember, to be able to work with a function, the first thing that you need to know is what is its domain? Why can you plug in into the function? Otherwise, you cannot do anything with it, okay? All right, so let me give you a theorem that tells you that such an interval always exists. So theorem, and this is the one that guarantees convergence of power series. And the idea behind this, to do it formally, to prove this theorem formally, is a little bit more involved. But in the case in which the limit of an plus 1 over an exists, the proof follows just immediately by using the ratio test example that we did above. Okay, so hopefully you believe what I'm about to write. So convergence of power series. So for a power series, center at C. Remember, when I say this, that means this is what needs to be in your mind immediately. Power series center at C, this expression has to pop up in your mind. Okay? Understand that this is just a shorthand for A0 times A1 x minus C plus A2 x minus C squared, etc. So then for a power series like this, only one of the following statements is true. So there are three possibilities. Only one of three cases can happen. Either it only converges at C, and that's it, it diverges everywhere else, or there is a number for which it's going to converge on an interval, which is centered around C, or it converges on the entire real number. Okay? So only one of the following statements is true. Okay, so number one, the series converges at C. The series converges only at x equals C. I'm gonna leave a space for the picture that I'm gonna draw. Number 2, that x is a real number. Well, let's see. Let me draw the picture here so you see what I'm saying. So what that means is that you have here the real line. Here is the point C, and then right here the series converges, and over here the series diverges. The series diverges, and we only have converges right here. Yes? So, and again, that's always the case. That should be clear to you, because if you put C for x, all of it becomes 0, and you get this number. Okay. So, all right. Then the other possibility is that there exists a real number. Let's call it R, which is greater than 0, such that the series converges absolutely for x minus C less than R, and diverges for x minus C bigger than R. So this should remind you what we're doing in the example with the ratio test. Okay. So the picture here is, if you solve this inequality, this means that x minus C is between R and negative R. Adding C everywhere, you're gonna get that x is between R minus C and R plus C. Okay. Or C minus R, no, R minus C and R plus C. All right. So the picture here is, here we have C, then over here we're gonna have C plus R, and over here we're gonna have C minus R. Okay, so far we have this, and then we know that the series converges here, and then on this portion diverges, and on this portion diverges. Yes? And I want you to understand that R is this distance. This distance equals R. Okay? Which, if you extend, you can consider the above picture as a particular case of this one. What will be the value of R in the above picture?
0.
0. Good. The above picture is the same as this with R equals 0. You're not moving anywhere. Okay? All right. So that's a second possibility, and then the other possibility is one of the three. Not, they are mutually exclusive. The series converges absolutely everywhere. The series converges absolutely for all x. Okay. So this number has a name. The number, this special number R. So the number R is called, who remembers the name? How do we call this? It's called the radius of convergence. Okay, so that's when in the problems they will ask you for interval of convergence, and they will ask you for radius of convergence. Okay, it's called radius of convergence. I want you to notice that in case number 1, R equals 0, and in case number 3, what will be R in that case? Good. In that case, we will say that R is infinity, okay? Because it converges everywhere. You have the center, but then the series converges everywhere. Do you understand this? So let's see. Moreover, let me go here. So what will be the interval of convergence in case number 1?
C. Or just.
The interval of convergence is just the point C, right? So yeah, you would just write this, like set notation, and you put C, okay? In case number 2, what's the interval of convergence? So C minus R to C plus R. And but then there is a little point that I need to put here. What is it?
You don't know whether you're including or excluding.
Plus or minus
Yeah.
the endpoints, right? Like you have to analyze the endpoints individually. Okay. So I'm gonna say here, not plus or minus, but.
Yeah.
But it's equal to that criteria.
So I guess I would say, okay, I would say these or these or these.
Whether it's equal to those endpoints.
You have to write all of them? You can't just like.
No, I'm telling you, it's just that I don't want to say plus or minus or something like that, and then you don't understand what I'm saying. So I would rather write this for statement. So that means that the interval of convergence, if you are in case number 2, the interval of convergence is one of these 4. I mean, these are not the same, right? So it's either one or the other. So it's one of these 4. It's either, because here I'm telling you that the 2 endpoints are not good. Here I'm telling you that the left endpoint is okay, the right is not. Here is the other way around. The left is not okay, the right is okay. And here I'm saying the 2 endpoints are okay. But that's something that you need to determine on a case-by-case basis. And what will be the interval of convergence in case number 3? What would that be? Negative infinity to positive.
No need for C if it's included so easily.
Say that again?
C isn't needed since it's in the entire undercall in the first place.
Yeah, I mean, the series always converges at C. Okay, do you understand this? So this is a theorem that tells you that for every power series, there is always the equation about interval of convergence makes sense. Okay, so you need to know how to find it. So let's do some exercises on that. So example, and typically it's either ratio test or root test. My advice is just do the ratio test, unless the sequence is super complicated, and then it's probably easier to use the root test instead. Okay, but the ratio test typically will do the job for you. But don't discard the root test. So determine the radius and interval of convergence. Okay, so from now on, I'm gonna write RC for radius of convergence. And what do you think I'm gonna write for interval of convergence? I'm gonna write IOC, but okay, let's go with IC. IC, okay? Interval of convergence, radius of convergence. Okay, so let's go. So first one. We do x to the n over n factorial. I mean, that's a special one for us, right? And let's do let's do x minus 5 to the n over 3n. Then let's do n factorial times x to the n. Hopefully with this, let's see. Yeah, so with this, it should be enough. Okay, so let's see, solution. So how do we do this? So for number 1, the idea is we are analyzing x to the n over n factorial. So we're gonna use ratio test. So we are after values of x for which it converges. That's what we are after. Okay, so the ratio test is what we should be using. Okay, so we need to look at the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. What is this equal to? Who can tell me how this simplifies?
X over n plus 1 to the absolute value of x.
So x on top, right?
N plus
N
1
plus 1
And n plus 1 on the bottom. Everybody okay with this? Should I write down how we obtain this?
No,
No?
if you want it.
Let me write it down. Just in case. So remember, you can write this as n plus 1 times n factorial. And this one is n factorial over x to the n. So these guys are gone. This one is gone. So we end up with absolute value of x over n plus 1. And because n plus 1 is already positive, we can just leave the absolute value on top and take the n plus 1 out. All right, now what do we do with this guy? What do we do with this expression?
The limit.
We need to take the limit, okay? So we take the limit as what? Have to be careful because remember, now we have n and we have x. It's as n approaches infinity, not x, n. Limit as n approaches infinity of absolute value of x over n plus 1. And we analyze what happens here. So what is this limit?
0.
This is 0, very good. Remember, this guy is a constant with respect to this limit. N is a variable that's changing here. That's becoming bigger and bigger and bigger, okay? X is whatever it is. What we're saying here is that regardless of x, this will always be 0, this limit, okay? So in particular, what do we know about this? It's less than 1. So what does that mean? It converges for all x, right? X can be whatever you want. This will always converge. So what's the interval of convergence? Negative infinity to infinity. What's the radius of convergence?
0.
Infinity. Yes? Okay. Take a look at the next one. Any questions? All right, so try number 2. Take attendance. I haven't taken attendance in a long time. Today is a good day for attendance. X minus 5 to the n over 3 times n. So try this and take attendance real quick. Okay, Carl Abbey,
Yes.
here. Gisela Costa, Elena, here. Corina, here. Joel Correa, here. Andy Diaz, Melanie Gavilanes, here. Ursundi, Daniel Herrera, here. Adam, Franklin, Jenna, no, wait, Zina, okay. Paul, here. I am here. Kyle, Laura, no. Okay. So what method should we use?
Ratio.
Ratio test. That's a good one to use. All right, so we need to compute the ratio of the n plus 1 term divided by the nth term. So that's times and then flip the expression. Okay, so in this case, notice that this guy cancel with this one and there will be an x minus 5 left in the top. Yes, and that's it. We cannot simplify anything else. So we are left with the absolute value of 3n times x minus 5 over 3n plus 3. Yes? Okay, so I always like to leave the absolute value where it matters. You know, the sign of this expression is determined by this term right here, because the whole stuff is positive. So this is what we get for the limit, for the expression, for the ratio. So now we're going to take the limit as n approaches infinity, right?
Yes.
Okay, what is this limit equal to? Absolute value of x minus 5.
Absolute value of x minus 5.
Good. So this limit is absolute value of x minus 5 because this piece right here goes to 1. Yes? This is the ratio of the leading coefficient, that piece. So that limit is absolute value of x minus 5. Remember, this is what we're taking the limit of. And now what do we need? We need this to be less than 1. Remember, we are after interval of convergence. So we know that when it's bigger than 1, it's going to diverge, right? So if we converge less than 1, then we need to investigate what happens when it's equal to 1. Okay, but at least it's going to allow us to get an interval now. Okay, can you tell me what is this interval? What is it? 4 to 6. Yes?
Yes. Yes.
Okay, good. Also think about it. Here where you're saying the solution here that all the x's around 5 whose distance is less than 1. So where must x be? It could be between 4 and 5 or between 5 and 6. If it's beyond 6, the distance is going to be more than 5. The distance between x and 5 is going to be more than 1. And if it's below 4, it's going to be more than 1 again. Okay? So 1 is, what is 1? That's your radius of convergence, right? Because that's the radius of your little interval. Anyways, my advice to you is you draw a picture of the interval and then you will see the radius right there. Just look at the center and then calculate that distance to the endpoint, and that's your radius. So solving this, we get x minus 5 is between 1 and negative 1. So adding 5 everywhere. So x is between 4 and 6. So far, this is what we have. So here is 5, and then here is, okay, I'm gonna write it like this, 6. Here is 6, here is 4. So far, this is what we get, okay? We are here so far. Now, we need to decide whether we should fill in the dots or not, right? Because we don't know what happens at 4 and 6. We don't know that yet because the ratio test does not tell us this. So that's how my interval of convergence is looking so far. So far, my interval of convergence is looking like this, 4,6, and then, plus or minus the parentheses. In other words, either put a parenthesis or a bracket. So we need to determine that point. I'm going to erase this so you don't get confused. So need to check the endpoints. Okay, so x equal 4. If we put x equal 4, what do we get? Let's write down you need to write down the series that you obtain. So if we put 4, what do we have? Negative 1 to the n over 3n, right? So we get the sum. Okay, so let's fix the example a little bit. We should have a 1 in here because with the 0, it's not defined, right? So we should have a little 1. Okay. So the sum from 1 to infinity of negative 1 to the n over 3n, that's what we get.
Yes.
So what can we say about this?
Alternating series test.
So this converges by alternating series test. Everybody okay with this? It's alternating, and then the term 1 over 3n, the limit is 0 and it's decreasing. So we come back here and we close the fourth, meaning we're gonna have a bracket there. Now let's play the same game with 6. If we plug in 6, what do we get?
1 over 3n.
We get 1 over 3n. So what do we know about this?
Geometric. No, convergence.
It converges by geometric series.
No,
Right?
it's 3 to that. It's not 3
It's
to
3
that.
times
right,
n.
right.
Oh, harmonic.
It's harmonic, right? It's a constant times harmonic, or you could do limit comparison test with 1 over n, right? So the point is that this diverges. You could say limit comparison test with 1 over n. Okay? Do you understand this?
Yes.
Or you can just say, look, this is just 1 over 3 times harmonic. So if harmonic diverges, then 1 over 3 times harmonic also diverges. There's several ways that you can argue this. So it stays open like that. So now we are ready. So what's the interval of convergence? So square bracket 4 comma 6, parentheses, good. And what's the radius of convergence?
1.
The radius of convergence is 1. So again, you figured out the radius right here, this distance. That tells you r equals 1. That's the same as this one. Okay? So when you find the interval of convergence, draw it. And you're going to see the radius. Okay? And just the distance between the center and the endpoint of your interval. Are we okay with this? All right? And then, let's see the last one was n factorial times x to the n. So sum from 0 to infinity of n factorial times x to the n. Okay, so what test should we use? Ratio test. So the previous one, you could have done it with root test if you wanted to. The limit would have been, because you have an indeterminate form and it would be a little bit painful, but that's okay. But this one, if you do the n root, you're not going to be able to do it because you have the n root of n factorial. What do you do with that? Okay? When you see factorial, it's ratio test all the time. So ratio test. So we're going to have n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. That's what we get. So after simplifying, what do we obtain? We get absolute value of n plus 1 times x. Yes? So that's just n plus 1 times absolute value of x, because that's the term that we don't know whether it's positive or negative, so we need to keep the absolute value in there. Now, what do? We take the limit as n approaches infinity. What is? Remember that I told you at some point I was going to use this notation, etc., right? Here, do you understand that means limit as n approaches infinity? Mm-hmm. Okay. What is limit?
Infinity.
Infinity. Therefore, what can we deduce? Exactly. So you have to be careful. So this means that, remember, technically, this limit is infinity provided that x is different than 0. Because when x is 0, before you even take the limit, this becomes 0 and then your limit is 0, right? So you could say, if you want to be technical, you either remember that they always converge at the center, and then this is just telling you what happens when you're away from the center, and then that's it. Or if you want to be technical, this limit is going to be 0 if x is 0, and it's going to be positive infinity if x is different than 0. Okay? And so from here, it follows that the only place that we get convergence is at this point, right? At 0. Everywhere else, it diverges. So converges for x equals 0 and diverges otherwise. So what's the interval of convergence?
Bracket 0 bracket.
Okay, so because it's a point, typically we just write a set like this, right? And what's the radius of convergence? So it will be 0. Good. Okay, questions? Do you understand how to analyze power series?
Yes.
Okay, good. So remember, moral of the story is to find your interval of convergence. Typically, if it's not infinity or 0, like those boundary cases, you will get something like this. But don't forget, most of the time, what happens with students is that you forget to check the endpoints. You need to check the endpoint because you don't know. Okay? So once you have your interval, you have to check individually the endpoints. All right, so we have a couple of minutes left, so that's good because this then will allow us to start getting closer to what we want. Okay, so these are power series, but how can we recognize them as functions? Okay, so I'm gonna do it the other way around. Okay, given a function, how can you express it as a power series? Okay, and we're gonna do the simplest case first. That's why I'm calling it power 1. And those are functions that can be turned into power series using, they come from a geometric power series, okay? They come from a geometric form, and then we can use it. All right, so you will see what I mean in a minute. So, geometric power series. Okay, and here the the remark is the following. So recall that if you have the sum from 0 to infinity of a times r to the n, what is this equal to? This is going to be a over 1 minus r, if and only if
The absolute value of R is less
the absolute value of r is less than 1. Okay? So when the absolute value of r is greater than or equal than 1, this diverges. Now, similarly, so if I replace r with x, right, then as long as absolute value of x is less than 1, we get a power series, right? Yes, we get a power series, and what is this equal to?
A over 1 minus x.
A over 1 minus x. Yes? And now we have a function. Now, you need to understand that this function has the same thing as this power series. They match as long as x is between -1 and 1. The moment that x is away from that interval, this doesn't make sense because it diverges, and this one makes sense. This is the function, right? It's just hyperbola kind of thing. So this equality holds as long as absolute value of x is less than 1. In other words, for this guy, what's the interval of convergence? From -1 to 1, and this time is parentheses, because when it's equal to 1, you know it diverges. Yes. Okay? And what's the radius of convergence? It's 1, because the center is 0, right? Okay, so because of this observation, let's ignore the a for a second, and then if you look at the function f of x, which is 1 over 1 minus x, you can write this as a power series. What would be the power series of this? The sum from 0 to infinity of absolute value of x to the n, right? And that this equality holds as long as this happens, okay? You need to understand this, because away from this interval, this makes sense, but this one doesn't, because it will be divergent, okay? All right, so we're gonna take advantage of this to take a bunch of functions that look like this, and so we'll be able to write them as power series, okay? So that's what I mean. So let me show you some examples. So example, write the function as a power series So write the function as a power series. And every time that you do this, it's not just telling me, oh, the function is equal to this series and that's it. No, you need to tell me for what values of x. Okay? Because in general, those two things are not the same. Okay? So write the function as a power series and find the interval of convergence. Okay? Once you tell me the interval, it's implied already what the radius is of convergence. So if you find the interval, I assume that you already know what the radius is. You know how to find it, right? Okay. So let's see. Okay, let's start with something. Let's see, we have time to do 3 examples. Let's do this one. Let's do this one. And then to hopefully get the idea, let's try this one. But this time I want to do it center at 5. And okay, let's try this 3 and then let's try this 3. Okay, so before I do the solution, so note, and this note is actually the idea for this type of problems, okay? So you see this formula that we have here, that 1 over 1 minus x equals that. The way that you have to think about this is as follows. Every time that you have 1 over 1 minus something, you can always rewrite this as the sum from 0 to infinity of that something to the n in absolute value. Sorry, wait. I don't know why they put this absolute value here. There should not be any absolute value in there. It's just I was too fixed on this thing. There is no need to put an absolute value in there. Okay, the absolute value has to be here, but not in there. So just make sure that you fix it. Okay, so and this equality holds as long as whatever this something is in absolute value is less than 1. Okay, so this idea is that you need to have every time that you have a function that fits this shape. If it doesn't look like this, you need to work with it and make it look like this. You already have experience with this when we're doing integrals at the very beginning, right? Manipulating the integral so it looks like 1 over, right? That kind of stuff. And then once you write it in this form, whatever expression you have in here, that's the thing that you're gonna take to the n power in your series, okay? I'm gonna be using this idea over and over again. And right here, you can figure out the integral convergence immediately because you just need to solve this inequality, okay? So let's use this solution. Okay, for the first one, I have f of x equals 1 over x plus 1. So this almost looks like what I need, right? I need 1 over 1 minus something. So the top is already okay, so that's fine. Now, instead of x plus 1, I'm going to put the 1 first, right? And instead of writing plus x, what should I write? Very good. Minus minus, because remember, you want the minus. So minus x. Yes? So now we're ready. So what is this equal to?
Minus x to the n.
The sum from 0 to infinity of negative x to the n, right? And this equality holds as long as absolute value of negative x, which is just absolute value of x, is less than 1, right? So what is this equal to? So it will be the sum from 0 to infinity of negative 1 to the n times x to the n. So, I mean, if you leave it like that, it's okay, but you know, it's good to realize that it's alternating, right? So that's an alternating geometry. You okay with this? And what's the interval of convergence? So remember, this happens as long as absolute value of x is less than 1. So what's the interval of convergence? Negative 1 to 1. Okay? All right, so let's see. Let's apply the same idea to the next one. So actually, I'm going to call this one number 3, and let me call this one number 2. That one will require a little bit more. Well, no, sorry. Number 2, number 3. So let's do 1 over x. Now, we cannot notice that the one on top, what's the center of the one on top?
0.
We managed to do the first one with center 0. Do you think it makes sense to try to do this one with center 0? Why?
Because then already you are to figure out how to get rid of 1. Or how to find the 1, I guess.
0 is not part of the domain of this function. This function is not defined as 0. So how come? Remember, we said that every power series is always defined as at its center, right? It could not be, it may not be defined everywhere else, but it's always defined at the center. So this function is not defined as 0. So we cannot hope that whatever form it takes as a power series, it will be defined as 0, right? So naturally, you won't be able to do this center as 0. We need to move to another center, okay? So let's do it. I guess the easier one here would be to do it center at 1. And how does it come up? Then here's what we're gonna do. Again, I want this form, right? 1 minus something. Yes? Well, I want a 1, but we didn't have a 1, so what we really had was a 0, so 1 minus 1. Yes? So far, we can write it like this. So far, so good?
Yes.
But then you can rewrite this as 1 over 1 minus x. Yes, by factoring out the negative. And now this is my box. Okay. So I don't like the way it is. Okay, we can fix that later. So let me just leave it like that. So this would be so far the sum from 0 to infinity of 1 minus x to the n. And remember, this is as long as absolute value of 1 minus x is less than 1. Okay? So we can use that to find the interval of convergence. Let's do it right now. So that means 1 minus x is between 1 and negative 1. Then subtracting 1 everywhere, you get that negative x is between negative 2 and 0. But then that means that when I multiply everything by -1, you need to switch the direction of the inequalities, right? So that means that x is actually bigger than 0 but less than 2. Yes, this is between 0 and 2. This is what we have. Now I want to accommodate this a little bit. How can we accommodate that? Because that's not how power series look like. They're supposed to look like x minus something, not something minus x, right? But that's easy. So we're gonna have, I can do a following. If I put a minus and then have my x minus 1. Yes, remember, you put a minus in front and you flip it, and then the truth is revealed. It was not clear at this point that it was an alternating series, right? But it's actually alternating. This is -1 to the n times x minus 1 to the n. Okay? So, and when does this make sense? This equality that we found for 1 over x, let me write 1 over x. So when does this make sense?
When x is not 0 or
As long as x is between 0 and 2. For example, if you are interested in this function for x equals 4, this is not good. This is not a good power series representation. Yes? Because that equality only holds here, between 0 and 2. All right. Are we okay with this? And then let me just do the last one, the gymnastics, which is some algebra. So that would be 2 over 3 plus 4x. But this time I'm telling you that I want c to be 5. So I want it to be centered at 5. Okay. So that means I need an x minus 5 to show up. Okay. So most of the things that I'm about to do is so that this happens. All right. Okay. So how can we get an x minus 5 showing up? Then I will worry about everything else. But I want an x minus 5 in that bottom. So how can we get that going? I should have a negative what?
7. No, 8.
Negative 20.
20.
So when you factor 4, you get x minus 5, right? So that's why I said, this, you have to think a little bit here. So I subtract 20, but then of course I add it, okay? Because it was not there. So far, this looks like 2 over 23 plus 4 times x minus 5. Yes? So I have my x minus 5. Now I need to make this look like 1 over 1 minus something. Yes? So what I'm about to do, we do that. The one on top is not a problem because when you have a number, you just factor it out and then you distribute it back into a series. It's not an issue. So how can we get a 1 here? We divide by 23. Because remember, if you subtract, then you're putting another term here, and I just want this to be one term. I don't need another term here. Okay? So I'm going to divide everything by 23. So divide by 23, divide by 23, divide by 23. So we have 2 over 23 over 1 plus 4 over 23 times x minus 5. Yes? Okay, and now, okay, I need a minus here, but that's easy. How do we make a minus show up? No, I don't want to flip this because then you have to do what it did there. Minus, minus. If you need a minus, just make this plus, you make it minus, minus. Okay, so that's not an issue. So we can rewrite this as, okay, I'm going to put this in front, okay, times 1 over 1 minus, and then minus 4 over 23 times x minus 5. Do you understand what I did? Do you understand why I did what I did? Right? Because it could seem random. Why did you add and subtract 20? Well, because I'm after an x minus 5. And I have a 4 here. When you factor it, I want something here that looks like 5 times 4. So that's where the 20 is coming from, right? Because after factoring a 4, I want a 5 left over.
You can't factor the 4 first, right?
Well, I mean, first is like this. Right? Yes, you could factor the 4 and then cancel it with this guy, but then you have a 3/4 here. You could factor the 4 first if you want to.
But it's another mess.
But for example, let's find a general form. If this was a 7, what should have been here? 35, right? And negative 35. pretty easy to figure out what goes in here. Okay? You just multiply by the number that you need, and then that's it. Okay, and then that's it. This is my box. Right? This is my box. So now what is this? That's 2 over 23 times the sum from 0 to infinity of my box to the n power. And when does this equality hold? As long as the absolute value of the box is less than 1. So this is gonna help us to find the interval convergence. Okay. Now it's just doing some aesthetic modifications here. So I'm gonna bring that 2 over 23 to the front, to the inside. I'm gonna separate these two guys. So I get a negative 1 to the n. Let's see, it's over here. So negative 1 to the n. Then we get the 2 over 23, and then we have 4 to the n over 23 to the n times x minus 5 to the n. Yes? Do you understand this? Okay. And then that means that we can rewrite this as the sum from 0 to infinity, negative 1 to the n. Let's see, we can make it a little bit more interesting. This 4 to the n, that's the same thing as 2 to the 2n. Let me put it here. Right? So when you multiply with this 2, it becomes 2 to the 2n plus 1. And this 23 with this one is 23 to the n plus 1. So it will be 2 to the 2n plus 1 over 23 to the n plus 1 times x minus 5 to the n. That looks better because now you can easily see what your an is. Okay? And what are the values of x? Let's solve that inequality quickly.
How are we able to get the 2 over 23? Right, the constant on the outside. Okay.
Okay, and by the way, if this was a 2x, then this would just be a 2x. It would be a 2 over 23 times x. That you take it out, and then you distribute it back in. The only thing is that then, well, if it's x, then it would be better to have an x minus 5, because then you have the x in here. But then if you make it so that there will be an x minus 5, then you will bump the power by 1. Okay? So we'll do that next time. Examples like those. Let me just finish the interval convergence here, which is solving this inequality. So the negative is gone, so this means 4 over 23 times x minus 5 is between 1 and negative 1. Multiply by 23 and divide by 4. So x minus 5 is between 23 over 4 and negative 23 over 4. And then you add 5. So 23 over 4 plus 5, which is that's 20, 43 over 4. And then negative 23 over 4 plus 5. That's 20, so that's negative 3 over 4. So that happens for x between 43 over 4 and negative 3 over 4. Okay? This right here is your interval of convergence. Parenthesis, negative 3 over 4, comma, 43 over 4. Okay. Questions? Do you understand this? It's going to be important because using this technique, we can, for example, find the power series of arctangent. Those are functions that are interesting to us, the power series of ln. Arctangent you will see pretty soon, but we're going to use this to find ln. Because one property that we're going to do next time is that now, because these are functions, you can take derivative, you can integrate. And it's pretty easy because these are like infinite polynomials. This is what they are, infinite polynomials. You differentiate and integrate the same way. Okay? So if 1 over x, equals this, right? If on this interval, if 1 over x equals this, when you integrate, what are you going to get? On the left hand side, you get ln. What do you get on the right hand side? Negative 1 to the n, that's a constant. You pass the integral through because it's a summation. You integrate this. What is this? X minus 1 to the n plus 1 over n plus 1. That's the power series of the natural log. Okay? So we're going to use derivative and integrals to come up with a power series of other functions like ln, arctangent. How do you do arctangent? The derivative is 1 over 1 plus x squared. Then you play this trick that we did, write it as a geometric power series, and then you have to integrate it to take it back to our tangent. And you will get your power series for our tangent. Okay? We're going to be doing all of these things on Tuesday.
Can you just go to the bottom really quickly? Sorry.
All right? And then we're going to do Taylor and Maclaurin series, and then that will be